Moving forward towards next, we have one of the most important and the oldest algorithms, that the naive Bayes algorithm. So now the name has two parts, base and the naive. Both of the words mean something specifically. So let's break it down. Base part comes from the Bayes theorem, a fundamental rule for probability theorem. Now, the naive part comes from a bold specifically assumption that the algorithm makes. We'll get it into a second. First, let me make sure that you should know what naive Bayes is about. This thing is extremely fast. Training is literally a single pass over your data, no iteration, no gradient descent, just counting. And despite being this simple, it rivals far more complex model on tasks like spam detection, test classification, and documentation categorization. It also works surprisingly well on a very little data and handles it better on high dimensional data like 50,000 words feature in NLP also. Okay, so now let's start that how Bayes theorem works first. Bayes theorem says that given a data point x, the probability that it belong to class y is proportional to two things: the prior probability of the class and multiplied by the likelihood of the class of seeing that data. In formula form, p of y given x equal p of x given y times p of y divided by p of x. Okay, so now the denominator p of x is the same for every classes. So whenever we are trying to find the most likely class, we can completely ignore it. Okay, classification just become finding the class y that maximize p of y times p of x given y. The prior p of y is easy. It just show how often each class appear in your training data. If 30% of your mail are spam, your prior for the sample spam is 0.3. The hardest part is the likelihood. P of x given y, your feature vector x might have hundred or thousands of feature. Computing them towards the full probability joint is computationally impossible. There's how we get into the naive part. Coming towards the naive assumption, that how it actually work, naive assume that all the features are conditionally independent in the given class, meaning once you know the class, you know the value of one feature that tells you nothing about any another feature. In reality, this is almost not true. In an email, if you see the word by, the word now is probably more likely to. Features are correlated, but naive bias just ignore that entirely. Why does this work anyways? Because even if the exact probability are wrong, the ranking of the class is usually preserved, and for classification, ranking is all what you need. Okay, so with this assumption, the joint likelihood factorization this into a simple product p of x given y equal to the product of p of x j given y for each individual feature j. Now, instead of one massive joint distribution, you just need one small distribution per feature per class. That's it. And now, that's a practical issue. When you have multiple hundreds of small probability together, you get numbers so tiny that computers round them to zero. That's called as the numerical underflow. This can be fixed in simple working in the log space. Instead of multiplying probability, you take the log and add them up. The result is the same rank but now numerically stable. Okay, so always use log space. Now you have your model. Each p of x of j given y depend on what type of features you are with. Okay, so here's where the variant come in. Gaussian naive bias is used for continuous real valued feature. You assume each feature follow a normal distribution within the class. During training, you just compute this mean and variance of each feature for each classes. During inference, you plug values into the Gaussian formula. Second one is the multinomial naive bias. For count data like word counts in a document, this is the classical spam filter variant. For each word, you count how many times it repeat across all the documents of each classes and gives you the likelihood. Third one is the Bernoulli naive bias for binary feature, where each feature is just 0 or 1, the word present or absent. The This is the key difference from the multinomial. Bernoulli explicitly penalized the absent features. If a word is not in the document, then the information is still used. Okay. Now there is one more critical problem, that what if a word never appeared in the training dataset of a given class? So this problem can be solved using the zero frequency problem. This is called as the zero frequency problem, and this can be solved using the Laplace smoothing. You simply add a small value alpha, usually 1, to every count before computing the probability. This ensures that no probability is even exactly 0. Alpha equals to 0 is called as the Laplace smoothing. Alpha less than 1 is called the Lidstone smoothing, which is general, and we don't use it many a times. Alpha is actually one of the most important hyperparameter in the naive bias, which we are using and can be tuned using the cross validation. Moving forward towards the section 3, where we'll be talking about the hyperparameter comparison and the key takeaway. First of the hyperparameter which we are using is the alpha, the Laplace smoothing parameter for the multinomial and the binomial and the Bernoulli NBs. Default it is 1, and for large vocabularies try using small value like 0.1 or 0.01. Second is the variable smoothing for the Gaussian NB only. Add a small value to the variance to prevent the division by 0. Default is 1 into e raised to the power minus 9, and usually you don't need to change it. Third one is the fit prior, whether to learn class prior from the data. Default is true, which is almost always what you want. Okay, but if your test data is very different on the class distribution, you can see the manual prior using the class priority. Third one is the binarize for binomial for Bernoulli NB only. Okay, it's for the threshold to convert continuous value into 0 or 1. Okay, so now one more important thing, that the naive bias or the logistic regression comparison. On comparing, we can say that the naive bias is a generative model, while the logistic regression is a discriminate model. With small amount of data, naive bias wins. It converges faster because it can make it can make strong assumptions which act like a implicit regularization. With large amount of data, logistic regression win because it doesn't carry the independent assumption baggage. Okay, so we have some of the points about the naive bias only, and let's move forward towards the limitation that you must know. The independent assumption is violated in every real data set, yet the classifier still works because correct ranking of the class probability is sufficient for the classification even if the absolute priorities probabilities are wrong. Second, the Gaussian NB can break down if you continuously feature are not normalizedly distribute. If they are skewed or the multi-model, in that case try log transformation of your feature. And finally, naive bias do not reduce the variance the way random forest does by averaging the many model. Its strength is entirely from the strong independent assumptions that act as a regularization. Okay, so here are some of the key takeaway points, and here we wrap up with the lecture. Thank you.